Okay, so now.
Yes, we see it.
So today I would like to speak about the a very special mathematical object, which is somehow new, which is so optimal that it almost should not exist. So I want to speak about the history of the Leech lattice. And so here's a portrait of the Leech lattice in the middle, or rather of it's somehow so. So it's a small part of this object, the shortest vectors of Leech lattice, which naturally live in a 24-dimensional space. And here they've been orthogonally projected into a 2-dimensional plane. And so this is how this pattern originated. And so today I want to tell you a story of this mathematical object, which is a little bit unusual and therefore interesting. So here, this is an example of a pure math object, which plays an important role in many modern mathematical theories. And at the same time, it owes its existence to applied mathematics and to technological development. And so mathematicians have discovered, like now embarrassingly for us, have discovered this object only after computer scientists have done so. And so the story of Leech lattice starts from the discovery of the Golay code in 1949. And here you can see this small blurry picture of Marcel Golay, who was a Swiss engineer, and somehow he is much less known than maybe some other computer scientists of that time. And this was the only picture of him I could have found, even though he have done some really amazing things. And one of them was discovering the Golay code. And so I will speak a little bit about the discovery, about what the binary code is, what was it good for, what kind of practical purposes it could serve. And then in 1965, so a bit maybe like 16 years later, the work of Marcel Golay was used by a Canadian mathematician, John Leech, who took this binary Golay code and used it cleverly so that he could construct an object in Euclidean, 24-dimensional Euclidean space, which is called the Leech lattice. And so some more years later, mathematicians have discovered that this lattice, it's not only has some optimal properties, for example, that it is a very good packing, provides a very good packing in dimension 24, but that it also has a lot of symmetries. And so symmetries of this lattice allowed, for example, American mathematician John Conway to discover new groups, what we call simple finite groups. And the simple finite groups, they were somehow this building blocks for the group theory that were still missing on the list. So that time, the program of classifying all simple finite groups was running full gear, and people have studied this, so to say, the groups that come in family. Then, to surprise of many people, some groups were discovered that did not fall into any of previously known categories. And then there was a question, have we found all of those? Is there finitely many of them? And so now somehow we know, or at least we believe, that the classification of finite groups is complete somehow, even though it's many hundreds of pages written by many people. And unfortunately, some of these people have already died. And so if once you're reading this classification and cannot understand all the details, unfortunately, there is no people to ask about all the details, but it's now more or less accepted by mathematical society that we do know classification of simple finite groups. And so finding these big exceptional groups, it was an important step. And yes, it's like at least 3 of these exceptional groups, they come from symmetries of Leech lattice. And then also the study of Leech lattice led to what is we know now a monstrous moonshine, or somehow, I tried to translate it Ukrainian today, and it was something like монструозне, це була гіпотеза монструозної несенітниці. Тобто таке дуже, насправді, Джон Конвей, він був відомий своєю ексцентричністю і харизматичністю, і він придумав таку цікаву назву для дуже красивої гіпотези, яку вже на початку 90-х років багато людей доклалися до того, щоб його довести. І, мабуть, останній гвіздочок це забив Річард Боршерц, але про це ми вже не будемо сьогодні розповідати. Це для вас, мабуть, на майбутнє, якщо хтось зацікавиться, ви зможете дізнатися також про цю історію. Але сьогодні історія, яку я хочу розповісти сьогодні, це, можливо, ось ця права частина моєї картинки, це про роботу Галея та про те, як Джон Ліч її використав для конструкції решітки, а також використати це як можливість для того, щоб дати багато означень. От, і на цій сторінці є деякі з особливих властивостей, які решітка Ліча має. Наприклад, якщо ми візьмемо ці найкоротші вектори решітки Ліча, які спроєктовані на цей слайд, то вони дають нам розв'язок. Okay, maybe I switch back to English. So the shortest vectors of Leech lattice, which are projected to this two-dimensional slide, they will give us the solution to the sphere kissing problem in dimension 24. And in the several slides from now, we will discuss what is the sphere kissing configuration and what we know about this problem in small dimensions, and also in which cases it is solved. And so also my contribution to this work, so that to this field is that together with Henry Kohn, Abhinav Kumar, Stephen Miller, and Daniil Radchenko, we were able to show that the sphere packing, which corresponds to the Leech lattice, is the optimal sphere packing in dimension 24. And so let us start slowly by giving definitions of all these objects I was talking about. And so let's start with the most basic one. So what is a dimension? And so we all know that one-dimensional space, it is a line, and a two-dimensional space, it is a plane, and a three-dimensional space, it is a space where we all live. And so as mathematicians, we can go farther. We can say that, what is the mathematical characteristics of all these spaces? So if you want to know give a location of a point of a line, we just need to give one real number its coordinate, and then we are defining the location of a point uniquely. And on a plane, we need to have two coordinates, so x coordinate and y coordinate. And if we have these two real numbers, then we know the location of each point. And in dimension 3, we have three coordinates. So we can continue like this, and we could say that point in a d-dimensional space, it is such a sequence of d real numbers, the d coordinates of our point. And basically that's all this is, so we have defined the dimension. And as mathematicians, we have a luxury of not worrying about what is the interpretation of these extra dimensions. There are some aliens living there, there are some physical forces acting. This is all irrelevant for us. For us, the dimensional point in d-dimensional space, it is just this sequence of d real numbers. And so another word I would like to explain is the lattice. So I speak about a Leech lattice. So what is a lattice? So d-dimensional lattice, it's a configuration of points in a d-dimensional space. And this configuration needs to have several properties. And I will not give a very formal definition of what a lattice is, but rather the idea. So first, this configuration has to be discrete. And so that somehow each point has some neighborhood where it lives on their own, comfortably far away from other points of configuration. Also, it needs to have somehow full dimension. If I just take a plane and draw a line on it and choose this integer points on that line, it will not be a lattice in dimension 2. It's not enough. They have to be in all we have to use all our space. And also this lattice, it's a periodic configuration. So if we move somehow it's a configuration that repeats itself after a shift. And so here is maybe the part which I will not give rigorously, even though it can be done. So that the lattice, it's a configuration that has maximal possible degree of periodicity. It's somehow, this is configuration which is as periodic as it can be. And it means that if we take any 2 points in our configuration and we draw a vector that connects these 2 points, then we can shift all our configuration by this vector. And then the configuration has to repeat itself. So this is what it means to be a lattice. So for example, in this example, we have a lattice Z2. It's a lattice which consists of all points with 2 integer coordinates in the plane. And so here I can choose any 2 points, for example, here point 0, 0 and point 1, 1. And so here I choose this vector and I shift all my configuration by this vector, and it has to perfectly repeat itself. And so here is another example of another configuration, which is still a periodic configuration, but it's not a lattice because here this periodicity is not enough. So I can choose here 2 points, and then if I make a shift, then my configuration by this vector configuration will repeat itself. But if I then do it somehow another time, then configuration will not repeat itself anymore. And that's why it's not a lattice, but just a periodic configuration. And so what are other useful notions that we have in d-dimensional space? So one of the important notions is the notion of distance. And so at this picture, we recall how the distance works in a 2-dimensional case. So here we just use this Pythagorean rule. If we have 2 points, x1, y1, x2, y2, and we want to compute the distance, then we compute the difference between, I think what is written here is not, this should be, sorry, x1 minus x2 and y1 minus y2, sorry. So we just compute the somehow relative differences between 2 coordinates, and so take the squares and compute the square root. And so this is how the distance between 2 points in d-dimensional space is computed. So this is what we call an Euclidean distance in d-dimensional Euclidean space. And now once we have a definite notion of a distance, then we can also define what are balls and spheres in this d-dimensional space. For example, the ball in with center x and radius r, it is the set of points such that the distance between x and this new point y is less than r. And the sphere, it's a set, sphere in dimension d, it's a set, sphere with center x and radius r. It will be a set of all points which are exactly at distance r from the point x. And so now, after we have defined spheres and balls, we can formulate the kissing problem in every dimension. So what is a kissing problem, or what is a kissing number? So suppose that in some d-dimensional space, we have one red sphere of radius 1, and we have many blue spheres of radius 1. And so now what we want to do, we want to construct a configuration out of them such that each blue sphere touches the red sphere, and blue spheres do not intersect with each other. They can at most touch each other. For example, in dimension 2, disk, it's a ball and sphere is a circle. And so we can put this red ball in the two-dimensional ball, two-dimensional disk into a center, and then it can be surrounded by 6 other blue disks of the same radius. And in dimension 2, it's not difficult to see that 6 is the optimal number. And so now same question can be asked in other dimensions. And also one can think of, we see that this question, it's a bit like a local version of a pecking problem. So we're trying to put somehow as many balls as possible close together, but here we don't try to go somehow far away and fill all the space, but we would just want to do it locally around one ball. And so already in dimension 3, this question turns out to be complicated. And there was a famous dispute between Sir Gregory and Sir Newton, where Newton told that he thought that kissing number in dimension 3 should be 12, so that we can, if we have one red sphere, it can be surrounded only by 12 spheres. But Gregory was not convinced about that. And he thought that, okay, probably it can happen that there is a space for one more sphere in there. And so what is the configuration in dimension 12? How can we put these blue spheres around the red one? So we can consider an icosahedron, regular icosahedron, and it's a polyhedra which has 12 vertices. And so we put a red sphere in the middle of this icosahedron so that the center of a sphere coincides with the center, for example, center of mass of icosahedron. And then we put blue spheres into the vertices so that centers of blue spheres coincides with the vertices of icosahedron. And we scale our spheres in such a way that the blue spheres will only touch the red one in the middle. And if we do this, it's not a hard computation to see that blue spheres will be far away apart. So blue spheres will not even touch each other. They will all touch the middle sphere, but will not touch each other. And so this way we can somehow place 12 spheres. We can also move, of course, because blue spheres are not touching each other, the construction is not rigid. We also can deform it a little bit. And yeah, but then somehow how to argue that we cannot deform them in such a smart way that eventually we free this extra space for one extra sphere. And so this problem was rigorously solved only in 1953, when mathematicians actually rigorously proven that no, however smart we are, we still will not be able to place the 13th sphere. And so this is what we know about the kissing number in other dimensions. So in dimension 2, we know that we have in dimension 1, our kissing number is 2. And in dimension 1, balls are really boring, they're just intervals. So it's somehow a very trivial question. In dimension 2, we have 6, the kissing number is 6, and this is an easy question. In dimension 3, the answer is 12, as I just told you about. In dimension 4, actually, the answer is 24, and it's also the dimension where we know an exact answer. And this result was proven in 2003 by Oleg Musin, so some 20 years ago. So in the mathematical terms, one can say quite recently. So that's a recent result for this type of problems. And then in dimensions from 5 to 8, actually, we don't know the exact number. We know only the estimates. We know that it's somewhere like in dimension 5, it's somewhere between 40 and 44. And it seems like a very difficult computational problem. And so as dimension goes up, the problem becomes more and more complicated. However, in dimensions 8 and 24, we already know the answer for quite a long time. So since 1979, we know that in dimension 8, the kissing number is 240. And in dimension 24, the number is 196,560. And this result, two results, they were proven actually the same year independently by Vladimir Levenstein and by Adlishko and Sloan. So this happens sometimes, that the problem was open for, I don't know, 1,000 years, and then 1 year, two teams prove it independently, but by a very similar method that became available around that time. And also this, best configurations in dimensions 8 and 24, we do know that it is unique. Actually, in dimension 24, we know that 24 is the best number, but we don't know that the configuration that we have is unique. But in this case, we know that what the answer is, what the best configuration is, and we know the uniqueness. And so in dimension 8, it turns out that there is a very special lattice called the E8 lattice, which is almost as exciting as Leech lattice, but I decided not to speak about it today. And it has 240 shortest vectors, and they provide solution for the sphere kissing problem in dimension 8. And shortest vectors of the Leech lattice give us the best kissing configuration in dimension 24. And so now we spoke about the kissing problem, which is like a local version of a sphere packing problem. So now let's talk about sphere packing. And so here I just recall again what is a ball in any dimension. And now what we would like to do, we would like to somehow take a very big box, which is big in all dimensions, and put there as many non-intersecting unit balls as we can. Or in other words, we want to find the densest possible configuration of balls in d-dimensional Euclidean space. And so let's see what are the solutions to this problem in small dimensions. So in dimension 1, ball is just an interval, and so we can cover 100% of a line with intervals. So it's a trivial problem. In dimension 2, actually we have a hexagonal lattice. And so we have this configuration, and it covers more than 90% of a plane. And in dimension 3, we know that balls can cover about 74% of the volume. And here's one possible configuration how to do this. This is similar to the way we stack oranges in supermarkets. But in dimension 3, the problem turned out to be very difficult, and it took almost 300 years to solve this problem. And so the problem, of course, of packing spheres is something very natural. I'm sure that people all around the world thought about this at some point, and maybe there are Indian texts, like ancient Indian texts, where this problem is discussed, and maybe somewhere there is an ancient Egyptian text still to be discovered, or ancient Chinese text where people would speak about a sphere packing problem, just because it's a very natural geometric question. And in our novel history, we know that this question was raised by Thomas Heriot, and the legend goes as follows. So Thomas Heriot was some scientist and a mathematician serving a British nobleman, and this British nobleman wanted to invade Spain. And so he asked Thomas Heriot how many cannonballs he can put into a ship. And Thomas Heriot started thinking about this problem geometrically, and he also thought that maybe cannonballs inside of a ship, they are a bit like atoms inside of a condensed body. And wrote letters about him, first to his patron, but also to a German mathematician, Johann Kepler, or German-Czech mathematician. And Johann Kepler thought that it's such a great idea that he also should write an essay about this. And he wrote a very beautiful essay about sphere packings, about atoms, about regularities in nature, and gave it as a Christmas gift to his patron of that time. So also without mentioning Thomas Heriot and his contribution. But nevertheless, the essay is very beautiful, and we can even find it online and read it. It's rather short, and so this is how the Kepler's conjecture became popularized. And of course, neither Kepler nor Johann Kepler nor Thomas Heriot, they did not really ask about proving or giving rigorous mathematical proof that this is so they both described what are the best packings, and they both observed that there is more than one, there are actually many seemingly optimal packings. And I think at that time, they would not be, at that time, the concept of rigorous mathematical proof was not formulated yet. So they just asked this as an interesting philosophical question. However, since then, somehow mathematicians became interested in the question like this. So let us somehow dive into these geometric configurations a bit more. So here I suggest that we are playing a game. And I can suggest you two different ways of stacking balls. So one of them is like this. So we already know, so what we will do, we'll build three-dimensional packing from two-dimensional ones. So we will be lazy. We will just, okay, we already solved problem in dimension 2. Maybe this gives us some leverage to solve it in bigger dimension. And an obvious thing to do is to take these two-dimensional solutions and to replace flat disks by three-dimensional balls. So thinking that this, like old disk, it would be, for example, section of our ball by a plane that goes through center, and then stack these balls one over another. And this is one way to do. So we already know that this triangular packing, regular triangular packing, is the optimal packing in dimension 2. So maybe we just should stack these packings one over another, and we can see somehow we have these holes between balls. And so if we try to put a new ball into of a new layer into each hole between balls of an old layer, we will see that that would be impossible. They will then intersect with each other. So, but if we choose and if we put new balls not into every hole but into every second hole, then there is a perfect alignment between them, and we can arrange a packing like this. Or we can do things a bit differently. So instead of going with optimal configuration at each plane, we can consider this square packing of balls. And so now, now each layer is less optimal. However, this packing does have some advantages. For example, this time we can put a new ball into each hole, and there will be enough of space. And also because the holes between this balls of this less dense packing are bigger, then our balls of our layers will go deeper. And so the distance between different layers, so each of the layers seems like less dense, but distance between layers is smaller. And so now you can try to guess which of these two packings you believe is an optimal one. And so when I'm doing this game in an auditorium, then it's possible actually to ask people, but I suggest that you just do it for yourself, maybe to think who is your favorite. Okay, and then I can tell you that they are actually equally dense. Both packings are equally dense, and it's not enough. They're not only equally dense, they're also geometrically equivalent to each other. And so they both constitute what is called the face-centered cubic lattice. So, and its packing, it can be, so a third way to construct the same packing is like this. So we take a usual cubic grid. So we fill our space with cubes in a regular way. So for example, so that the vertices of all these cubes, they have all integer coordinates. And this way our space is filled with this cubes of with side 1, and so now we are packing not with unit balls but with balls of equal balls of smaller radius. So now we place our balls in the following way. First, we have red balls, and we put our red balls so that the center of a ball coincides with the vertex of each cube. You remember we have this infinite pavement of space with cubes, and for each of our cubes we take its vertex and put the red ball with the center of this vertex. And also cubes, they have faces, and faces have centers. So blue balls have the centers of blue balls coincide with centers of faces of our cubes. And so now we rescale our balls so that red balls and blue balls have the same radius, and they only touch each other and do not intersect. And so what we get like this would be this face-centered cubic lattice. And so now let's try to see that this packing is actually the same as two packings I have constructed before. And so I will demonstrate this by coloring my balls differently. So if I color the balls like this, so I take the lattice and I divide it into layers. And so each layer is perpendicular to the main diagonal of the cube. I choose one cube, choose its main diagonal, and draw a plane which is perpendicular to that one. And this is how I layer my lattice. And so this way you can see that this will be actually very similar to what I've done first time, because each of this two-dimensional lattices now that will be this triangular lattice. and I will be stacking triangular layers together. Or I can color my packing in a different way. So now I am choosing the plane which is parallel to one of the faces. And this is how I define my layers and color my layers. And now each of the layers, they will be cubical. They will have the square lattice, and these square layers will be packed together, the same as I've done in the second configuration. And so what I was aiming to demonstrate in this way, it is that geometry is hard. And so even in three-dimensional space where we all live and we have so much experience, we are still pretty bad in three-dimensional geometry. Probably you experienced this in your stereometry class in high school. Or okay, so here I have my theory. Maybe it's because we cannot fly. I think it's because we are just walking in 2 dimensions. And maybe if we were birds, then we would be much better in, like our geometric abilities would be much better. And so here's one more excuse for like, why is Kepler conjecture so difficult? Why is it a difficult problem? Another reason is that the solution, this optimization problem, and solution to this optimization problem is not unique. Actually, we have uncountably many sphere packings of maximum density. And one way to see it is to come back to our very first construction of a dense packing in three-dimensional space. And so you remember we constructed our packing from this two-dimensional triangular layers of triangular lattice. And at each time I've told you that we cannot put new, for example, here a new green ball into each hole between blue balls. There will be not enough space. So we have a choice. We have a shift. And somehow if we are doing these shifts consistently, then we will get a nice lattice. But we also can do this choice in somehow arbitrary ways, or any way that pleases us. And then we could make configurations that are not periodic, that are not lattices. And so they will be geometrically different. And so this is how we are arriving these uncountably many geometrically distinct configurations. And so despite all these complications, in 1998, Thomas Hales was able to resolve Kepler's conjecture. And solution of this conjecture, it's an interesting story on its own. For one reason, it's that this was one of the first mathematical proofs of an important result that used the law, heavily used computer computations. And so there was a big discussion inside of mathematical community, should it even be accepted as a proof? Or I think what maybe how people, or I hope how people see it now, it also sees like what kind of new, if you use computational power, what abilities that opens to us. And this started many interesting projects, like, for example, Thomas Hales was a part of this flying speck project of writing more. So first, what he have, after solving the Kepler's conjecture, he also written a formal proof of Kepler's conjecture. And this formal proof could be verified by a computer, where a computer is really verifying the proof step by step, that each step satisfies the axioms of arithmetic. And now there are several interesting projects like this, where the aim is to formalize as many theorems as we can, and also formalize as many proofs as we can. So there is an interesting, there is this flying speck project, there is Lean project, there are maybe some more competing languages and software in this case. So now, I think now it's an interesting, very interesting venue. But we will not go much deeper into this topic. So now we will go back to the story of Marcel Gallet, and to the story of error correcting codes, and what are error correcting codes, and why are they related to sphere packings. Okay, so error correcting codes, they were invented somehow during and after the Second World War. So a lot of this work was done actually during the Second World War, but then it was secret, and it was published only several years later. And here are the people who are, and also here's Claude Shannon, Richard Hemming, who are sometimes seen as the fathers of computer science as we know it now. And actually the Claude Shannon, Richard Hemming, and Marcel Gallet, they all worked in Bell Labs around the same time. And that time, Claude Shannon wrote several influential papers that actually shaped the computer science as we know it today. For example, he wrote a paper on mathematical theory of communication. And so also Richard Hemming was one of the first people who suggested some explicit error correcting codes. And so Marcel Gallet was a very somehow creative person who came up with really, really good error correcting codes. So in particular, the binary Gallet code. So what is all this about? So here is a general communication system, or I would say a very simplified communication scheme of a communication system as first suggested by Claude Shannon and then also changed by myself or adopted by myself. So, okay, so here how it goes. So we have some source of information. For example, person is speaking by phone, and then the signal goes into a transmitter, like your cell phone. And then the signal is sent to the receiver. And here what can happen is that there is some source of noise. And you can think that all this was done in case of 1940s, and that time maybe technology was somehow less advanced than it is now. So yeah, you could think there was a lot of problems where things do not exactly work how expected and all kinds of errors occur. And so there is a transmitter, there is a receiver, and then from the receiver, there is a somehow destination. So somebody who listens to that message or who decodes that message. And so here's an example. So my original message, I want to send message like just one digit, one. And then digit one is transmitted. But then because of an error, this one has flipped to 0. And so then my message is ruined. So how to prevent this from happening? And so in this scheme, what is reasonable to assume is that this noise, it exists, but it is somehow a little bit under control. So certain amounts of errors is introduced, but not too much. So for example, if somebody deliberately just ruins all my messages, there is nothing I could do about that. But if it is some natural cause and this maybe errors occur with some probability, and this probability is somehow over control, then I can try to come up with an engineering solution to this. And so here's a very naive scheme. So I can just send my digits, I can just repeat them several times. So for example, if instead of sending 1, I repeat 1 3 times. And then I transmit 1 3 times, and then there is an error, but maybe the error doesn't occur too often. And so out of these 3 digits, only 1 was changed. And so what people who receives this message, it sees, okay, so first it will understand if it knows my coding system, it will see, okay, so these 3 digits are not all identical, therefore there was an error. And this is called error detection. So person can say, okay, there is something wrong with this message. But then also a person can think, okay, maybe the error was not too big, and maybe only 1 byte was flipped. And so in this case, it's somehow safe to assume that the original message was actually 1. And so this is the idea behind, but somehow repeating every byte several times, it's just a terrible coding system. It's very inefficient. And so the problem which Shannon, Hemming, and Gallet were working on is to how to suggest more efficient systems for coding. Okay. And so here is a system which is called the binary Gallet code. Here it's, okay, here is the list of possible code words. And so what is somehow, it is actually much more efficient than one I showed you before. So here each original message has length 12. And each transmitted message has length 24, so twice longer. But then each transmitted, when I send this transmitted message, what I send are not any words, but only words which are some combinations of these words that are written in my matrix. And so the person who receives the message, it can actually, there is an easy procedure to check. the word which they receive, is it a code word or not? And if it's not a code word, then person knows that, okay, the error has occurred. And so this way, so this code, it can detect up to 7 errors. So it happened that I sent this 24 bytes, and 7 of them might get corrupted. And then still person would be able to say, okay, so this is, the error has occurred. And if there are only 3 errors, then this error also can be corrected. Then person has a good chance of guessing what was the original message. And so how is it achieved? It means that among these 2 to the 12 code words, they all are somehow different. If you take any 2 of them, then there will be at least 8 positions where they have different values. And so if I am changing somehow, if I take one code word and change any 7 positions in it, I will never get another code word. And so, yeah, so the person who receives message will know that it was corrupted. And if I make only 3 errors, then because there should be like at least 8 distinct ones, they can choose code word which is closest to this corrupted message, and this would be the decoding process. And so, okay, so here's how the what a connection to sphere packing is. So here's what is a geometric interpretation of error correcting codes. So here we again, as if, okay, we like geometry, want to have some space, and here space, it will be all words of fixed length. For example, length d. So remember, all points in Euclidean space, they are all sequences of real numbers, and in Hamming space, our points are these sequences. Only each coordinate, it's not a real number, but it is either 0 or 1. And now we also have a useful notion of distance here, and here it's quite different from Euclidean distance. So here the Hamming distance between 2 words like this, it will be the number of positions where my words have different letters. So here's an example. I have these 2 words, 0, 1, 0, and 0, 0, 0. So here in the first position, they are identical. In the second position, they are different. And in the last position, they are identical. And so it means that the Hamming distance between this word here and this word here is 1. And it turns out that, okay, this distance, it's very different from the Euclidean distance that we all know and we are used to. However, it still has some similar properties to what kind of properties distance has. For example, it satisfies the triangle inequality. So if we measure distance between point x and y, it will be always smaller and equal than distance between x and z and y and z for any third point z. And this turns out to be a very important property, actually more important than some other properties that Euclidean distance has. And so here, this is what was somehow a brilliant idea of Claude Shannon. It is that somehow error correcting codes, they are actually sphere packings only in Hamming space. Or to be more precise, a code that corrects R errors, it is, in a sense, it is a packing of balls of radius R, only not in Euclidean space, but in Hamming space. And so, okay, so this is maybe right now, this is a bit of a like philosophical observation, but on practice, it did turn out to be very useful because many concepts that we know from geometry, they could be transferred into this context. And many methods that work in either constructing or proving theorems about sphere packings in Euclidean space, they also work for error correcting codes and vice versa. And okay, so now what was the, so maybe this is what was the contribution of John Leech? What was his construction? So John Leech, he knew about Gallet code, and he found so it's not a trivial construction how to go from Gallet code to the Leech lattice. And in a book of Conway and Sloan on sphere packings, lattices, and codes, I think, or no, on the groups. they have 24 different constructions of Leech lattice. So once you know that Leech lattice exists, you can construct it in whatever way you want. But it was really important that somebody have done it first. And so this is how John Leech have done it. So he constructed it in a very rather explicit way by just giving the vectors which belong to the Leech lattice. And so he introduced this normalizing factor, and then each vector in the Leech lattice, it had 24 integer coordinates, and these integers had to satisfy certain interesting relations. So I think it's not so easy to come up with a construction like that, but somehow he managed to do it. So first, this integers have to satisfy this condition. So the sum of all numbers had to be okay. So the sum of all coordinates is equal to the 4 times each of the coordinates mod 8. And also now, if we place this, so if we take any vector in a Leech lattice, look at this 24 integer coordinates that become integer after normalization. And we look at each residue class modulo 4. And we are drawing a binary word of length 24 by following rule. So we would write down 1 if at place I, if this coordinate AI belongs to our chosen residue class. And so all vectors in the Leech lattice, they consist of all such words where for each residue class modulo 4, all these words are words in a binary Galilei code. So it means for each vector in a Leech lattice, we will have we can produce 4 different words for each class modulo 4 by this way. And each of these words has to be a word in a binary Galilei code. And what he was able to prove that if we make a construction like this, and it actually be a lattice, so it will satisfy this nice maximum possible periodicity property. And also this lattice will have co-volume 1, or in other words, if we on average, we will have 1 point of this lattice per unit of volume in 24-dimensional space. And distance between 2 distant points would be bigger or equal than 2. And so now if we have a lattice such that distance between any 2 distinct points is bigger or equal than 2, then we can construct a sphere packing. And we do it in the following way. So this sphere packing, it will take unit balls, and we place a unit ball with a center at each point of the Leech lattice. And because distance between distinct points is at least square root of is at least 2, so these balls, they will not intersect, they might only touch each other. And so the theorem that I was able to prove together with my collaborators, with here's Henry Kohn, Abhinav Kumar, Stephen Miller, and Nikola Radchenko. So we have shown that no packing of equal balls in 24-dimensional Euclidean space has density greater than the density of the Leech lattice packing. So the packing which is obtained from Leech lattice in this way. And so, okay, so this is all I wanted to tell you for today, and please ask your questions.
Okay, let's thank Marina for the beautiful lecture. І, Марина, в тебе є ще 5 хвилин на запитання?
Є. Може, в мене навіть є 10 хвилин.
Тобто, можна запитувати голосом, чи можна запитувати в чаті?
Я думаю, як зручніше.
Як зручно. Може, я почну і запитаю, ти пояснила нам, чому градка Ліча є самою оптимальною, і ти ще сказала, що градка E8 майже оптимальна.
Ні, градка E8, вона теж оптимальна в своїй розмірності для багатьох проблем. Просто для своєї лекції я мала обрати. Я вирішила, що в мене не буде часу, щоб про обидві ці решітки. Я обрала мою улюблену.
Yeah, so I wanted to ask, why did you use майже? Why did you say almost? Is there any meaning why
No, that was not a mathematical statement. It was
Okay,
just
okay,
a philosophical statement. I don't know.
Okay.
No, I
okay.
think E8 is as good as it can be in its dimension. So it just, yeah.
Okay, thank you.
It was almost the best in my personal ranking of lattices. So.
Okay, thank you. Okay, more questions, please.
Yeah, there is a question in Q&A.
Okay, there is a question in Q&A. Okay, let me see. Okay, so here is a question from Vasily Dolgushev. Is there anything special about the sphere kissing problem when the dimension is power of 2 to the n?
Not clear. It's not clear. I think it, of course, if dimension is power of 2, then usually somehow more symmetries can happen in that space. Sometimes we can construct better configurations, but it's somehow, but which one is the best? It does not help much if it's a power of 2.
Mm-hmm.
And they're all still like in the dimensions where we at least like have good candidates. They're all quite different. So there is no industrial way to solve all dimensions which are powers of 2. So I think like usually for geometric problems, have even dimension is good, maybe because I don't know, for some, yeah, because more symmetry exists, we can, I don't know, interpret real numbers as complex numbers, some algebraic methods work, but then there is no somehow simple way or some clean way how to prove all of them.
Okay, thank you. Next question is from Boris Holikov, and he's asking, does there exist some asymptotic bounds for sphere packing problem in n dimensions?
Yes, there is a bound. So there are somehow upper bound for the density of sphere packing, and we know that the density of sphere packing decays exponentially as dimension goes to infinity. And the best bound we have, you know, for a moment is a Kabatiansky-Levenstein upper bound, and Levenstein is the same Levenstein as in the theorem I already mentioned today.
Mm-hmm. All right. All right. Next question is by Vasily Ustimenko. What about analog of root system for Leech lattice?
Yeah, so maybe for this, if you're really interested, maybe it's better to consult some of the Borchards' work. But yeah, so Leech lattice, it does not have like a root system in a classical sense, but it is still somehow related to this vertex operator algebras, and it might have this more general root system. But then this somehow it's a very interesting mathematics, but also not an easy one. So it's yeah, so of course I also like when it comes to representation theory, it's a very, very beautiful and deep theory, and also not an easy one.
Okay, thank you. Next question is by Martin Leshko. He says, I heard that it is connected with the method of magical functions. Can you elaborate on it a bit?
Yes, so today I did not speak anything about the proofs, and maybe I will not be able to somehow give a concise answer to this. But essentially the idea is as follows. It's this idea of, sometimes it's called linear programming, and the same idea that got us, solved the kissing, sphere-key kissing problem in dimensions 8 and 24. And it goes like this. So if sometimes we want to prove a geometric statement about points, we have to construct a function with special properties, function that satisfies certain type of inequalities. And so this was done for the sphere kissing problem. And in that case, the special functions, they all have to be polynomials, and therefore it's easy to search for polynomials with special properties, or at least this in this situation. And for the packing problem, we also had to construct a special function, but it's not a polynomial anymore, it's just a Schwarz function with some very such the function itself and its Fourier transform satisfies certain inequalities. And so this is, yeah. But then maybe to go deeper into this, there should be another lecture.
Okay. Okay, thank you. And the next question is by Mykola Seminyakin. Are there any interesting generalizations or deformations of sphere packing problems?
Yeah, so there are many versions, and like what is interesting, what is not, it's of course for matter of taste, but yeah, there are many ways to go. Like we can pack by spheres, only spheres having different radius, or instead of packing with spheres, it's possible to pack other like convex bodies or maybe even non-convex bodies. And yeah, so these are all difficult questions, and in a sense also interesting. But like there are also, maybe it goes in a bit different direction, and it's here like the question of density is not so relevant anymore. Like some people number theory study Apollonian packings. It's when you are not only just like take spheres of any radius, but you just somehow cover all space with spheres of radius that goes to zero, and then somehow the density becomes infinity. But then there are also many interesting geometric and analytic questions you can ask about this Apollonian packings. So yeah, there are plenty of geometric questions like this.
All right, let's see, any more questions?
Yeah, maybe I can ask a question by voice. So well, in the kissing problem, you can consider a problem with radius ratio, which means that the balls that are kissing a given ball have a different radius, and the ratio of radii is a certain real number. And
yes.
If you have a highly symmetric configuration and you choose this ratio to be extremal for which it exists, is it other results where you can actually prove that it is the best for that ratio?
For some of them, I think also, so you mean like a generalization of kissing problem, right?
Yes, but maybe
so it becomes something like what is called the spherical code. So
yeah,
like
so maybe it gets easier when the ratio is extremal, so that you have a highly symmetric configuration which is also rigid.
Yeah, so I think it's somehow here also there are many open questions. It's like there is no simple answer here. So I think this type of problems they also done somehow one by one. Unfortunately, there is no really industrial approach to this. Of course, it's interesting to study this like jump cases where the configuration suddenly becomes rigid, but it's also it seems like it's a difficult question. So typically there are upper bounds, lower bounds, and in small number of examples we have exact bounds. And so there is a community of people who work on this, or at least worked some time ago. I think Neil Sloan had some papers about this, but it was probably a long time ago. There was, for example, there is a Christine Bachok, Frank Valentine. At some point, they had many results on this, but I don't know, maybe now they moved to slightly different topics. So, but yeah, so here it seems like this, of course, kissing problem, it's not, if we're changing the radius, it will be not much different from others. And yeah, and also I think if you want to study symmetries, like which symmetries we can have on a sphere, or what finite groups can be embedded into an orthogonal group of given degree, I think if you are a representation theorist, this seems like a trivial question, but if you are really like into these geometric questions, then it suddenly becomes a very difficult question. And I think there is no somehow nice answer to this.
Okay, thank you very much.
Thank you. Any more questions? Yeah. If no more questions, let me just remind you once again that in August, Maryna is going to give lecture series on the same topic, but at a more advanced level in Kyiv, and everyone is welcome to register for that. All right, maybe let's thank Maryna again. Thank you very much.
Yes, so thank you very much. It was a great pleasure to meet with you today. Yeah.